So we are going to start with a presentation by Elodie Maignant, who is going to reenact the PhD to this defense that happened a few weeks ago in Sophia. And so
I just hope that it's not as formal as it was. So if you want to interrupt at any time, please do so. And yeah. All right. So yeah, I did 2 weeks ago, and it's basically exactly the same slides. So my thesis was on the question of geometric learning. So the question of learning nonlinear data. And in this question, I worked on some methods based on barycentric geometry. The final title is this one, Barycentric embeddings for geometric manifold learning. So work that I did was Xavier Venec and Alain Trouvé, that is probably lost somewhere. So I think these first slides are for you not so useful, but I will still go through it. So why do we have sometimes nonlinear data? And I'm asking this to a population that works on shapes. So I think that's not too hard to answer. So basically, when we have like the Euclidean statistics that don't work so well or don't provide correct enough estimates, but we also have this, the mic is not on. Okay. Okay, great. So great. So it doesn't work well, and you also have some a priori information on your data, and you want to use them to make the estimates better. But this a priori that you have is a nonlinear one. So then you move to nonlinear statistics. So for example, I have 2 examples in my thesis that are mainly shapes, but also graphs. So a first example on graphs, I'm studying these 2 graphs. And if I consider the graph represented by its adjacency matrix, I just average the 2 adjacency matrices. I get a graph like this that has 2 hubs, but in terms of averaging the strategy of the 2 airlines, I would want an airline that is quite similar to the 2 first. So obviously not this. So it really depends on the model that you want to put on your data. Okay, how do I go? Okay, great. Same with shapes. If you just consider it 2 protein configurations and you look at the shape they have in 3D and you put just a position for each atom, and this is your matrix, and you just average the 2 matrices, then if the 2 shapes are not aligned, what you get is not something that you want. Like if you look at it a bit closer, there are some deformations, some structure that are not well oriented or that have gotten smaller because of the averaging and so on. But if you have some information on what your data structure could be, like this, then probably you can come up with the better modelization to start with. So here, for example, it's well known that for the shapes, we have to align them beforehand, and it's even well known in the biology community. So per-crystalline analysis is, I guess, older than shape analysis in the end. So the alignment is well known, but if you want to do it in terms of mathematical model, then you want to go to something that is, for example, in terms of invariance, quotient space. Quotient space are not necessarily linear, depending on what you have. And if you do this, so representing your 2 shapes in this quotient space, so up to some rotations, but also maybe also transformation, that what you get is much better. Okay, so that's non-Euclidean data analysis, and depending on the model that you have, then you can have a distance, so you have a metric space, or you can even ask for a bit more. So although classical modelization is Riemann manifolds, so where you have the Riemann metric, so not only geodesic, but also more sophisticated tool like parallel transport that can allow you to do transfer learning, this kind of things. So yeah, okay, I guess this is pretty clear for all of you. And then, so we have this type of data that are modeled in a nonlinear space, and we want to adopt the methods of dimension reduction to this data. So we start from linear dimension reduction, which are the classical methods that work for Euclidean data and that are based on a global model. So a typical example is the PCA. We have the data set in the Euclidean space, and we want to look for a subspace that approximates the data set. This is what I call linear dimension reduction. So global model and Euclidean data. Now we want to move into two directions. First one is, of course, according to what I just said before, non-Euclidean data, and this we will call it geometric learning. So, for example, generalizing PCA to non-linear data, so to manifold valued data. That's a quite well-studied question. Another direction is moving from the global to a local model, and this is the question where we know that our data, they are modeled in some space, so can be a Euclidean space, but within this model, we are also looking for some hidden structure that is probably a local structure, so locally linear, for example, and that's the question of manifold learning, that this probably should be better called submanifold learning, so we want to learn the so-called submanifold that could approximate the data, but that we don't know. So if we combine the two, now we could imagine that we have non-Euclidean data, so living in, I don't know, in some manifold, and we want to learn a submanifold of this manifold. So we want to go for a local model, but also non-Euclidean data. And what we want to do is to work basically on the two green blocks, so working with the non-Euclidean data, both with global and local model, and I mean the two of them come together. So, and all right, one last thing in this introduction. I didn't explain yet what is the barycentric word. So basically, if you take the linear dimension reduction and you look at PCA, so that's the most well-known method, what you want to do, as I said, is that you have this data set of point in Rn, and you want to fit a linear subspace to this data set. And this linear subspace, you're looking at it as just a vector basis. So you're looking for a set of orthogonal vectors that will span this subspace, and you optimize on these vectors. But another way to look at it is to say, it's generalized well, I mean, more or less, to nonlinear data with the notion of geodesic component and geodesic subspaces. And then you have all these methods that you know that are principal geodesic analysis, tangent PCA or geodesic PCA, etc. All of this. But another way to look at this model, still in the Euclidean case, is to say, okay, we are looking for a subspace, linear subspace that is described not by a set of vectors, but by a set of points. So now we are looking for an affine basis of this set of points. Of this subspace, and we are optimizing on points rather than optimizing on vectors. And so in the case of PCA, the two way of seeing it give exactly the same results. But of course, now if we want to generalize this to nonlinear data, then it will give a different results. And that's what we're going to do. So the idea of working with points rather than vectors, comes from multiple intuitions. But first thing is that sometimes the vectors in terms of the dataset are not so easy to interpret, while the point could be easier to interpret directly. And it's also that this affine characterization will characterize probably different things in the dataset. So, for example, it's not easy to reconstruct the distance from an affine point of view, but the angles or the alignment properties are really well characterized by this. So that's just a different way to see and to look at it, and of course it will give different results, and that's what we investigated in this thesis. So, okay. So today, defense program was to speak about the first two extensions. So first go from this model that you just saw, where we have the subspace parameterized by a set of points, and we want to extend this to non-Euclidean. Yes.
Sorry.
Yes, of course. This.
So there's a constraint on the points A, A0, AK, on the side that if they are
So, okay, a priori there are no constraints. We are looking for any set of points, but of course, set of points can describe the same subspace. So in terms of optimization, then we will have to add some constraint to make it.
You want to make it as small as possible because it's all.
You could ask for this. Let's say if you don't ask for this, then it's not well parameterized for them because you have different set describing the subspace. I would say we would rather look for the more extremal points. in what we do later. Like, okay, I will come back, but let's say we can constrain this set of points, of course, otherwise it's not well defined, and there are many ways of constraining it, and I will come later to one possible way of constraining it that makes sense. But it's true that like this is kind of conceptual, but it's not well defined. Yes. Okay, so we start with this model that is in the Euclidean. So first case, Euclidean data, it's a global model. We look for one subspace, and we want to extend this to non-Euclidean data. So more specifically, if we have a data set on a manifold, then can we still define this set of points that we parameterize a subspace or not, and how can we do it? And so then the idea would be to go to the local version of it, but to go to it, we have to first define, just in the Euclidean case, what is the local model. So what could be, like locally, we would estimate this kind of subspace, and then we would have to kind of connect each of the subspace together. And the thing is, once we have defined this, so the global model in the non-Euclidean case, and we have defined the way of doing it locally, then if we combine the two together, it's very easy to get the last block. So that's why I'm not presenting it yet. Okay, so there are two questions. How to generalize the barycentric model to non-Euclidean data, and how to glue local barycentric models together. Okay, and I will start with this question. It's a bit more easier, I don't know. Yeah. So we have this, so the same slide as before. And the idea is to generalize this thing to a data set that lives on a manifold. We could also think of more general spaces, but we start with the manifold. So to do this, basically the first notion that we have to generalize is this weighted sum here. So the sum of the WIAI, and this is a barycenter, a weighted barycenter. So we have to generalize the notion of a barycenter to a Riemannian manifold or to a manifold. So to do this, the question that we ask first is, this is a weighted sum, and of course the sum is not defined on the manifold. So how can we define the same object but intrinsically? And this question, I mean, it's already known. We know that, for example, the mean or weighted mean is also the minimizer of the weighted sum of square distances. And this is intrinsic, because if we have a distance, we can divide it in another space. And this definition is exactly the definition of the weighted Fréchet mean. So if we have a metric space, then we can define the mean as a minimizer of the sum of weighted sum of square distances. And of course, this problem does not necessarily have a unique solution, or it can, in practice, go a lot into local minima and so on. So it's not so easy, but we can define it, and that's what we have. But we are not going to use this definition because having already a minimization problem to solve just from the definition of a barycenter is not very easy to manage computationally, because then we are going to ask for even more. We are going to constrict on this barycenter. So we went for a definition that is a bit more relaxed, and this is one of exponential barycenter. So it's basically the first order condition of the weighted Fréchet mean. So if you derive the previous optimization problem, this is what you get. You get that, okay, that the weighted sum of the log, and this is here the Riemannian log. I hope it's okay, yeah, probably. The Riemannian log, then it has to be 0, and that's the critical condition. And then we say if a point satisfies this critical condition, then it is an exponential barycenter. And of course, there can be, with the same weight and the same points, several barycenter that satisfy the condition, so it's not unique. But compared to the previous definition, is that we replace the minimization problem by just critical condition that we can solve with a Newton procedure worst case, and that we can also kind of cleverly integrate as a constraint in another bigger optimization problem. So it's just easier to manage, and that's why we go to this. But it's a weaker condition. So if we have this, we don't necessarily have the weighted Fresnel mean. Okay. Yes. I mean, a good remark is that this definition, the weighted Fresnel mean definition, they all coincide in the Euclidean case with the usual weighted mean, weighted sum. So I would say everything is fine at this far. Yeah. Okay. So we have the barycenter, and now this subspace that we're going to optimize. Well, we are going to define it just as the set of all possible barycenters. So you take a basis, so A0 to AK, and you take all possible real weights that sum to 1. Then you consider the barycenter with these weights, and the set of all these barycenters is going to be called the barycentric subspace. And that's the generalization of our linear or affine subspace spanned by the basis. And this barycentric subspace, it is a very weird object. So in a very general case where we have a manifold that can be anything, the subspace can also be more than anything, like can be very irregular, can be stratified, can be a lot of things. So it's not a very nice object to work with, but it's defined, and in simple cases, it's still quite okay. So first of all, what we will do is that we consider the completion of this space just to ensure basic properties that we want. So in practice, we consider the completion of it. And in the case of Rn, it's perfect. It's exactly the same as before. So it's the affine subspace spanned by the basis. And in very simple case, so like constant curvature manifold, like the sphere, that is just what we expect it to be. So if we take barycentric subspace of 2 points on the 2 sphere, then what we get is the great circle that cross the 2 points. And same if you go to the hyperbolic version. Okay, so we have defined the barycenter. Now we have defined the barycentric subspace, and our methods, which is in fact the method developed by Xavier Penec, which equaled barycentric subspace analysis on manifold, is just really this PCA, a fine PCA version, but on a manifold. So we look for a basis and a fine basis, A0 to AK, that span a barycentric subspace, minimizing the projection error. And that's the definition of it. In practice, it's a completely different problem. And that's, I guess, where my job started, is to make it work or not, but to understand how it works. And for this, we considered a very specific case, and this is the one. Okay, sorry, I forgot about this slide. Okay, sorry. Okay, I will just finish my sentence. So we considered the one of graph. So we looked how to implement this method on a set of graphs. But just before, what I defined to be in the barycentric embedding, and I mean, that's good that I don't forget about it because it's in the title. It's okay, you have this method, so you found your subspace and you have your projection on your subspace. The problem is that the subspace, as I said, barycentric subspace can be very ugly, can have a very complex geometry. So you don't want to have a representation in this space, because in the end, it can be even more complicated than before, at least in the case of nonlinear data. So what we do instead is we say, okay, we have this basis and we have this set of weights. And what we are going to do, well, we're going to transport the basis in a very simple space. So for example, RK, and we're going to look for, I don't know, images of the basis. And once the basis is fixed, then we can use the same weights to reconstruct a new representation, but this time in RK and not in our barycentric subspace. So is this, let's say it's completing the method to end up in something that is very standard and having a low dimensional representation on a simple space. So I don't know if this is very clear. So if you have any question, please ask. But yeah.
So I don't understand why it simplifies the problem. Why it solves the problem. If you have a barycentric subspace which is like crazy, which has a crazy geometry, how can the embedding or express? So I don't have the intuition.
Okay, maybe I can do the drawing. So in the simple case where you have the data set is in Rn, so let's say R3, and you found, I don't know, a plane like this that approximates your data set, right? This, what I'm doing here is just saying, here I have a basis of 3 points like this, and they are points in 3D, but I can take a representation of this point in 2D, and then I can reconstruct the projection just using the weights that I have. So if you do this with the very standard case, then what you get is just, you get the representation in 2D. So you get 2D coordinates, because you can just transport the basis, and then what you construct is just an affine mapping, and that's it. But now imagine that you're on the sphere, and let's say, I don't know, it's 50 years ago, and you don't like working on the sphere, I don't know, something like this. So you have your points, the representation that you get is on a great circle like this, you have this projection, but you wanted to have something in completely linear space. So what you're gonna do is you're gonna say, okay, I know that this is A0, A1, and there are 2 points spanning this, and all the projections are defined by weights. And I'm gonna say, okay, I'm gonna transport this and this thing on a B0 and B1 this time on a line. And all the other projection, we reconstruct them with the weights, the same weights, but no, as a combination of these 2 points that are on a line. And what I get is no point on a line. So it's just a way to say, we have a representation that is simply defined by weights, but if we want to work in the space that we have, knowing that the geometry can be very wild, and that in the end we don't even know it. If we start in a very, I don't know, let's say non-constant curvature manifold, what we end up with is barycentric subspace can be quite disconnected, can have a lot of things, and so on. So we don't really want to end up with a representation in this. We want to end up with something very simple. So we say, okay, I just transport my basis, and the weights that are in the end the most precious thing that we learn here, we're going to use them, but in a simple space. So here we go from the circle to R, for example. But we can imagine here having something even more.
But the mapping may be not injective or. Oh, yeah, it's.
So to ensure that it is, for example, injective, we have to ensure that these two things are that the way we map the basis is already injective. So the way we choose the basis, the new basis, we have to be a bit careful. So in practice, what I do is I preserve the pairwise distances within the basis. So I say I have this A0 to AK, and I'm going to do some multidimensional scaling, for example, just with the basis to find images, just to ensure that I don't end up with a basis of lower dimension, for example. But it's called an embedding in the machine learning community way, in the sense that it's not a very well-defined map. It's just a representation, I would say. But I do the best that I can to keep it as you say, as good as possible, so injective if possible, and so on. And what I want is that in the very standard Euclidean case, that it's just an affine transformation. I just want this. So in the end, you kind of go from an affine space to another affine space. It's just that the first one can be a big one. So what you build is really an affine transformation somehow, the way you do it. But yeah. Okay, so that's what I was saying. So this embedding, it preserves barycentric coordinates. And as I was saying, so the second part, the second row is really an affine mapping. You go from an affine space to an affine space, and you just transport the basis and all the other points accordingly. That's really another way to define an affine map. So that's it. And if it's injective if the basis is transported to a basis. Yeah. So that was just a way to say, okay, in practice, how do we do to get a representation out of our model? Yeah. Okay. So yeah, back to the graphs. Okay, another question is, we have the method is well defined conceptually, but if we take a practical example, does it work? And does it give something good? And is it fast enough? And so all these questions. So we study the example of graphs. So we have a population of graphs, like you would have a population of shapes, and we want to do some dimensional reduction. So for example, on this set, it's a very easy set because it's small in terms of number of nodes. So just by the eye, you can already say something. You can say that you have 3 groups. Complete graph groups, then a group of star-shaped graphs. So here, the intuition that I want to give a bit is that, in fact, you have some invariance acting here, and the invariance is the invariance by permutation of the nodes. And what we want to say is that in the second line, all these graphs have the same structure. Like, they are not permuted exactly in the same way. Okay.
Can you just reshare the screen?
Yes, I can.
Often maybe. Yes. Yeah.
Hi. Okay. Great. Sorry. Okay. So yeah, here in the second row, what you have is that you have all the same structure. And what this is saying is that you're studying a quotient space somehow. Last row is just cyclic graph. So you have 3 groups, and within the group you have some variability, small variability, and this is exactly what we expect to characterize with our method, hopefully. So, okay, yeah. Okay, so this graph are called unlabeled because you don't care about the way the nodes are ordered, or you don't care about the labels that you can have on your nodes, or you don't even have labels, or you have Persian labels. You can have a lot of things, but in the end, you want to work independently of the labels because either you're not interested, either you don't have it. So I was using in the very first slide the example of mobility networks, more specifically airlines. You have a strategy that consists in a node being an airport and an edge being the number of flights, for example, between 2 airports. And you are not interested in, Air France having a hub in Paris or Lufthansa having a hub in Berlin. You just want to say, okay, they both are based on the main hub, and then it's kind of a star-shaped graph. And we want to say, okay, then this is the same strategy. While if we use EasyJet, for example, we study EasyJet, then it has a lot of hubs everywhere because it's more of a locals company. It's not very much based in any country. And we want to say, okay, these two are different. In terms of modelization in the literature, it's it's the most natural one. So we say, okay, we have a graph represented by an adjacency matrix, and we are going to quotient out by the group of permutation acting on the nodes. And that's our space of unlabeled graphs. And so it's just saying, okay, these 2 things are the same. Yeah. So we have this quotient space, and this quotient space is not a manifold. It's mostly a manifold. It's a manifold if we exclude all the graphs with some symmetries, where, of course, the action has different isotropic group and so on. So the whole space is a stratified space, and for this reason, it has been studied mostly only as a metric space and not further. Okay. And moreover, the metric itself is also very complicated to compute because it's based on the graph matching problem. So just the problem of aligning 2 graphs according to permutation is a problem with no exact solution, and it's a combinatorial problem. So when you start having a lot of nodes in your graph, it's very expensive. So for this both reason that you don't have much more than metric setting, and that even the metric, the distance itself is hard to compute, expecting to even try out our methods on this space was impossible. like we tried, but soon we understood that it was going to be just too complicated for what we wanted to achieve anyway. So we thought of going to another modelization of the graphs. So we introduced this spectral graph spaces. So this is something I did with Anna Calisano, that maybe some of you know, that is working a lot on graphs and graph analysis. So we introduced this space where we relax the action of permutation by the action of orthogonal matrices, which is a bit bigger. And this is to address the graph matching problem, which is very expensive, and we want to replace this combinatorial problem by a continuous problem. So now we have to align according to an orthogonal matrix. It's the continuous optimization problem, so we expect it to be implemented quite faster. And that was the first idea. Now, the thing is, okay, it's really a relaxation, and it's not like magic relaxation where in the end we get a solution that is a permutation. That's not true. So if we optimize this, we get an orthogonal matrix that aligns the two graphs, and it's not going to be a permutation matrix. So I'm not solving the graph matching problem here. I'm just saying, okay, I'm going to go to a different model that is probably a bit less informative, but probably also much more efficient. And it still makes a lot of sense in terms of graph theory, because what we are doing here is that we're identifying two graphs that have the same adjacency matrix spectral. And this is kind of the beginning of spectral graph theory, where we try to characterize a graph by its spectrum. So the spectrum of either its adjacency matrix or Laplacian matrix. And the spectrum does not characterize completely a graph, which means that two graphs with the same spectrum can be different in terms of permuting the nodes. So you can get two different graphs. But if the number of nodes increases asymptotically, then this is true. So that this is true that the probability that two non-isomorphic graphs have the same spectrum goes to 0 when you have an infinite number of nodes. Just to say that this, in terms of structure of the graph, still makes sense, and it's not completely weird to go to this space. So we call it the spectral graph space, logically. It has a very well-defined distance, so it's just the usual quotient distance, and in fact, it has the quotient distance as explicit expression, so we can compute explicitly the rotation that aligns a graph on another, or adjacency matrix on another, and in the end, the distance is just given as the distance between the two spectra. So. What? They are ordered, yeah. They are ordered the same way. So, for example, yeah, from smallest to greatest.
And just to be very clear, so the metric between the adjacency matrices is like an M2 metric?
It's a Frobenius. I mean, yeah, it's a Frobenius norm. This, yeah. Usually, this is the one that is used in graph analysis. But I think we could also. It has been explored using different metrics with different powers, for example. But in the terms of quotient spaces, is usually, even with the permutation, what they start with is the Frobenius metric. So simplest metric on adjacency matrices. So yeah, and this this spectral distance that we see here, it's not new. What we do here is connecting the dots, let's say. But this distance has been studied for a long time, even with any possible powers. So spectral distances are well known in the graph theory. So we are just kind of connecting the quotient space with things that already exist. And that's just the beginning, because we have further identification. So we have a result that says our graph space, our quotient space, in the end, it's completely isometric to the cone of ordered eigenvalues. So this W, that is also called Veil chamber, And okay, to this isometry, I will just detail a bit. On the whole space, on the whole quotient space, we have an isometry in terms of the distance. But if you take the the space of regular graphs, so the space of graphs that have all distinct eigenvalues, that's also the main stratum of the space. Then we have this isometry is also Riemannian isometry. So we have the main stratum of the space of all graphs with distinct eigenvalues. They identify in terms of Riemannian isometry with the space of strictly ordered eigenvalues.
Yeah. Another question, because I'm familiar using the spectral decompositions of
Yeah.
the Laplacian.
Yes.
But here you're talking about the
adjacency
matrix.
Yeah.
And like, what are the conditions that you need on the adjacency metric to be sure that everything works? Like,
Here we consider symmetric adjacency matrix.
And nothing more, and there is no weird condition.
Nothing more. Yeah. The reason why we didn't work on with Laplacian is because the action doesn't preserve Laplacian. The action of rotation. But both spectra are well studied in the community of graph theory. So, yeah, there are a lot of results even for adjacency matrices. So we have this identification, and we are just saying, okay, starting from now, we are going to work in this simple space, which is the cone, and we are going to work with geodesics that are just straight line. So the geodesic connecting to graph is isometric just to a straight line between the two spectra, basically. And I mean, you can go even further. You can think about the parallel transport and everything. But the main result that is important for us here is that the geodesics of our graph space, they are uniquely defined everywhere on the space, even if it's not a Riemannian manifold completely, because it has some stratification. The geodesic, we can define them everywhere. So even if you take two singular graphs, a graph with multiple same eigenvalues, there are still a geodesic connecting them, and it's uniquely defined. And it's a geodesic in the sense that it really minimizes the length. So, and that's a very important result, because the run that we had in the previous space is that it was not. First of all, the metric was hard to compute, but it was also not the case that we would have a unique geodesic between two any graphs. That was not true. And here it's true. So that's the main improvement that we have here. And it's true, and it's also very easy to compute, because everything is working in this cone. So linear space with just some linear boundaries. That's very nice. Okay. So now we can go back to our closely to our barycentres. So, for example, the mean of Fauché mean of a set of graph is just you take the mean of the spectra, and your mean graph, your average graph is the graph with this spectrum, with the average spectrum. So the main is simple. I mean, I'm just giving an example of the theorem, but and a bit more complicated. So barycentric subspace of a set of graph, then it's gonna be in isometric in this cone to a polytope, a convex polytope, which is defined by a. So you just take weighted sum of the spectra. That's what you have, and of course you have some condition of inequality, because you want to stay within this cone of ordered eigenvalues. So that's where the inequality comes from. And each inequality, they correspond to a half space. And when you intersect all this half space, what you get is a convex polytope. Yeah.
And, how do we turn your spectrum into a...
Yeah, that's a very good question. So that's a very practical question that we can avoid in our method. I will explain why, but we still studied it. So if you have a spectrum and you want to go back to a graph, you have, of course, many graphs that are possible. I mean, many matrices that are possible. And there are matrices that make sense in terms of your data set, and matrices that don't make sense. So for example, if you have the graph and you take the diagonal matrices, the spectrum, and you take the diagonal matrices with all the eigenvalues, it's perfectly I mean, mathematically it's correct, but if now you plot the graph, you get a graph that is completely disconnected with just weights on the nodes, and this you don't like so much. So we studied more particularly the question where your graphs, they have no weights on the nodes. So they have a diagonal that is 0. And if this is the case, then the spectrum that you get is going to be of trace 0, right? Now, if you get a spectrum that is summing to 0, then you know that there will exist at least one matrix with diagonal 0 that has this spectrum. That's a linear algebra result. So what we're doing in practice, if we need to go back to the graph, is that we're just looking for the one of these matrices of diagonal 0 that has the spectrum. And it's not necessarily unique, but at least it makes more sense because in the end, at least you don't have this weight on the node that was the worst thing that we could expect in terms of representation. But that's what we do generally in practice. But with our method, we have a way to avoid this. I will just come to it to avoid the question.
Yeah, but so am I right to understand that basically you gaussian by a group which is very, very large? So
Yes.
basically you had an n by n connectivity matrix,
Yes.
and you say that you reduce everything to
To
a
the
vector
spectrum.
of size n.
Yeah.
So
But I mean, initially we really
it's
want.
very destructive.
Yeah, exactly. I agree. Initially, we really wanted to relax. I mean, the permutation action, honestly, it's not possible to work with. It's just too expensive. If we can't even compute distance efficiently, then it's kind of a problem. So we wanted to go, to avoid this and to just relax the permutation group. We have not so many options, and the smallest that we found was the rotation group. But reducing a graph to its spectrum is not so reductive. Like it is a lot if you have very small graphs, but once you start to have very big graph, it's not so reductive anymore in terms of what we are interested in, which is in the end the structure of the graph. The spectrum is still a good descriptor. Like it's not a complete descriptor, but it's very good. So it's not so bad. And if you give me 5 more minutes, you will see that it doesn't work so bad in the end. So before selling it, we waited till the end to see if it worked. Yeah.
Just like when you say that, so you have the assumption that the trace is 0.
Yeah.
What does it mean in terms of graph?
So it's more that we start with graphs that have no weights on the nodes.
Okay.
So it means that the diagonal is 0, and then
There's an equivalence.
it's not really an equivalence, but what we have is that if you get spectrum that's summed to 0, then you can find, that there exists at least one matrix,
You can find a representative.
at least one, yeah, that has a 0 diagonal, which is already nice.
But
You can also find many of them. It's not only one. So that's why it's not yeah. Yes, sorry.
On this code, then now just do PCA instead of barycentric analysis.
So PCA and graphs?
No, now you work in the spectrum, right? Now you have reduced your graph to the spectrum in this code.
Yeah.
Could I just do PCA on them and get like a linear subspace and intersect it with the code to get the same result?
You could do PCA, but okay, give me 5 minutes. I'm going to explain that. Okay, so we could do PCA in this code. I mean, we are also aware that the framework is more than just our method, and it could be used for something else. Because in the end, everything is simple. So we're also saying that if you want to do something with this space, just do it. But our initial goal was still to do barycentric subspace analysis for a very specific reason, is that there is a way to do it such that the descriptor that you get are going to be within the data. And that's a very powerful thing. So, okay. Oh, yeah. This is a convex vector optimization problem, so it's very nice. It's a projection problem is nice. Okay. All right, so we have our previous data set. And now what we're going to do is we're going to say we're going to do barycentric subspace analysis, but we are going to enforce our point basis to lie within the data set. So we're going to look for 3 points within the data set. That probably also answered the question of Barbara from the beginning. So there are many ways to constrain them, but one way that we do it, especially that was the initial reason why we were interested in this method for graphs. Why Anna was interested is because generally in graph, whatever you use, you have a very intense problem of interpretability, even more than on shapes, I think. So that, for example, they already have a lot of different PCA methods defined, but when they look at their component, it's not so easy to interpret what you have, like in terms of graphs. So she was looking for within data methods or archetypal method, this kind of method that put some constraints on your descriptors so that what you get in the end is easier to interpret. And BSA, it's very easy to define it as a within data method. So you just say, okay, I'm going to look for the point within the data set. And if you do this, for example, with the data set and you look for 3 points, so subspace of dimension 2, well, what you get are exactly a graph of each structure, which is actually very nice. And this PCA wouldn't do it. With PCA, you would get some 2 components, and looking at the components sometimes can just not give anything very obvious. Especially, I don't know, if the graph, like if the set is 2-dimensional and mostly Gaussian, you really need the 2 components, and on each component you don't really much see something, like it's not so easy. But here what we get is the 3 points saying, okay, these 3 points, they somehow characterize our data set. And now if we look at the representation in 2D, using this embedding, but here is actually the subspace itself because it's flat. Well, we see that then within each of the 3 groups, we have the small variability that can be visualized in 2D this way. So the result that we get with this method is double. We have a representation in 2D, but we also have this 3 descriptor that is a bit kind of a clustering type method, or a bit like a k-means or something like this. So that's why we don't do PCA, but we do BSA. And you can also constrain the point to be extremal, so you can constrain, you can try to minimize the projection within the convex hull of the 3 points. And if so, then you get points that are a bit more extremal, so you go a bit more towards archetypal analysis. In this dataset, it doesn't change so much, but in some datasets, it can really make a difference if you constrain them to be to describe a convex hull. So okay, so that's what we get, so all I explained before was just for this, but I'm also aware that the framework can be used much more generally. But honestly, I mean, for the graph, it was really new to have this kind of methods. So we are quite satisfied with it, I think. And then that's just one example we experimented in other data sets, like the airlines and so on. Yeah.
So can you just, so you have your 15 graphs?
Yes.
And then can you just repeat the
Okay.
steps?
So we have these 15 graphs, and we're going to describe them by spectrum somehow. I mean, in our Gaussian space, it's the same. So you get 15 spectra.
So you have 15 spectra?
Yeah.
They don't have this, the first row, they don't have the same spectrums?
No, but they will have very similar spectra, but not exactly the same because there are different weights on the edges.
Ah, okay.
Yeah, there are weights that just in symmetry.
Sorry.
Yeah, sorry. This I didn't very much mention. So yeah, we are just in a structure of graph that have weights. Otherwise, of course, it wouldn't make so much sense, I think. So this is our graphs, and again, we perform BSA, but we perform BSA in the spectrum space. So using the spectra with different graphs. And what we do is we're going to look for a basis of 3 points within the dataset. So we just explore the dataset to find 3 points that define the subspace of minimum protection error. And what we get is these 3 points, and when we have this, we also have the projection that is defined by weights for each graph. And we use these weights to plot them into T. Yes?
And so 2 questions on the algorithm. So the first one is, how expensive is it to compute the full spectrum?
It's a
Spectrum on such a graph?
It's a usual decomposition of a symmetric matrix.
Okay.
So it's expensive. Then
Yes, okay, so it's expensive to compute all of them, I assume, because usually, you know, when you have a big graph, you say I can compute the top k.
yeah.
But here you really try to.
I mean, if we have very big graphs, we could also say, okay, we are not interested in the full spectrum, and we're going to say, okay, these are, let's say, in the middle we have a lot of 0, and then we are interested in the extreme negative, extreme positive eigenvalues, and that's why we're interested in.
And then to perform your BSA, is it something like a bit like a greedy algorithm? You know?
So here it's super greedy because we explore everything. But what we could, I mean, what I could think of is that we.
So what do you mean? What you mean we explore all the triplets?
Yeah, exactly. No, but on this it's very. We did it because we have the right to. If you have a very bigger data set, no. But what we could do is to say, okay, I'm gonna try to get some prior information on an approximative clustering, and then I'm gonna look for the triplet in each cluster.
Recording in progress.
Absolutely. Yes, that's fine. So, I mean, that's a very naive way of doing it, but of course, if we have a lot of graphs, we would want to do some prior steps where we get some information, like even approximative, and then we explore within this. So something like this. Yeah. Or, something like something would be less complicated idea, but still makes sense. The question was with the clustering approach.
Like here, if you were doing some, the extra, you know, the clustering approach instead of approach.
So yeah, what I was saying to Jean was asking, are you exploring all the triplets? Yes, but I wouldn't if I had like 100 graphs. But what I was saying is that we can maybe do prior steps where we do some clustering on the spectra, and then we explore only with this information. So we look for a point in each cluster to save time. So it's very greedy, but it's also very powerful in terms of description. So that's why we still like it. And you could imagine also that we are interested in a data set where we don't have so much graphs. We have like high dimensional graphs, but not so many of them. Such that, for example, deep learning method wouldn't do so well. Because I guess that's mostly our angle of attack generally, is to look for small data sets. Otherwise, we have to admit that the deep learning does well, so. Okay, it's reconnecting.
Although too much with the connection. Then.
Yeah, it's okay. But that's the end of the first part actually, and I don't know. It's already late, so I don't know if I do like a pitch of the second part or if I go completely through it. I don't know. It's up to you. It's interesting. Yes. I mean, you'll have to tell me probably. Okay, great. I do it then.
Recording in progress.
Yes.
Sorry.
Okay. It's completely different though, but yeah.
Yeah, there may be one question.
Okay.
In the general theory, so like you said in linear space with like barycentric analysis and PCA is the same thing.
Yeah, in Euclidean case, they're the same.
What about the like Riemannian manifold case?
They're not the same. You're not going to get the same space. Yeah. Well, I mean, usually in case it was proven that you get exactly the same space. Of course, if you don't have constraint like this, but if you don't constrain your 3 points, you will get exactly the same subspace. Exactly the same. But in a Riemannian manifold, it's not true. Yeah. And I mean, specifically, you don't have the thing that the mean will belong to the space. That's not true.
Okay.
Yeah. Okay.
Don't bother with it.
I'll try not to, but it's still coming back to me. So, is this the last time maybe I do it? Okay. Oui. C'est du rhum. Ouais.
Il y a il doit y avoir un travail du labo.
Ah, oui.
Non. De toute façon, là, c'est avec la partie 2 où tu fais. Ah, ça marche un petit peu, on fait quoi pour de base.
Okay, it's close. Si, je pense.
Je suis là.
Non? Okay. Ah, c'est... Ah, ok. Okay. Okay, so second question is the question of, we go back to Euclidean data to start with, because we have to start somewhere. And we have this global model, so we look for just one subspace. And now we want to look for locally for a subspace, and then we want to glue the subspace together. So, I mean, the question has already been asked in PCA, for example, how can you do local PCA and glue them together? And it's really not an easy question. But here, more specifically, we start from this method called local linear embedding. So it's a manifold learning method from 2000, and it has a lot of similarities with barycentric space analysis, in fact. So we have a set of data points in our N, and we start by defining the notion of locality, or what is being local. And this is the classical approach. We build a neighbor graph. So in manifold learning, it's mostly always start with a neighbor graph. So for each point, we select neighbors, can be the k-nearest neighbors, or the epsilon ball neighbors, or anything like this. Yes, I think I will just... yeah. And now we're going to do, in fact, what they do is really to fit a local barycentric subspace to the data set. So they say, okay, I have this xi and it has some neighbors. And what I'm going to do is just, I'm going to say, okay, if my data set is locally linear, or is sufficiently linear in a very local neighborhood, then probably my point is going to lie very close to the subspace that crosses its neighbors. And this is exactly the barycentric subspace of its neighbors. And if so, then projecting this point on this subspace shouldn't be a too bad approximation. So I'm going to approximate each point by its projection on the barycentric subspace of its neighbors. That's what the methods do. And this projection is described by a set of weights, and the method retrieves these weights after the step 2 and goes to step 3, where with the same weights, it builds an embedding. So it says, no, I'm going to look for a new set of points in my RK, so for example, in the plane. And I'm going to ask for this set of points to, as best as possible, match these coordinates. So I'm going to ask for yi to be as close as possible to the weighted sum of its not of its neighbors, but of the image of the neighbors of xi. So I'm going to try to respect as much as possible the weights that I had before. And this is my embedding. And at the end of the method, it builds an embedding. And in the first example, it worked well. And when they started to explore it a bit more, it didn't work anymore. And the main problem that they faced was that the solution that you have is not unique. So if you do this, then you have many embeddings that have the optimal cost. So you would have embedding that looks exactly like what you want, and embedding that don't look at all like anything you want. And the reason why is that barycentric coordinates, they are not descriptive enough because they are invariant by affine transformation. So in some cases, if you just take the same points, but you apply some local affine transformation, or even a global affine transformation, then you get exactly the same weight, so you get a solution with the same cost. And that's a problem, because if there is one thing that you want to ask in this kind of method, is that the embedding is unique, at least. Even if you don't know what it is, you have to be in. So we soon noticed that it was not unique, because it was not obvious in the literature either that we would encounter this problem. And the way they deal with it is to add some penalization to the projection problem, such that you get approximate coordinates, barycentric coordinates, and that with these approximate coordinates, in the end, in practice, it gives a unique embedding. But what it does in terms of modifying the embedding, we don't really know. So that was their solution, and that's how it ended, the story of local linear embedding. But we just saw a lot of similarities with our methods. That's why we got interested in it. So first of all, we wanted to generalize it to Riemann manifold, but soon we had to solve first the problem of uniqueness of the solution. So here I considered a very simple case where the projection is projection of distance 0. So in fact, our point does lie in the barycentric space of the neighbors, such that it is the barycenter, so it is the weighted sum of its neighbors. And I also consider the case where there is at least one optimal solution of cost 0. So it's a very ideal case, but even in this case, there are a lot of things that happen. So that's why we start with this. So I look at this thing. So what we are building is basically a map that preserves local barycentric coordinates. And local refers to the neighbor graph. And it's also true that affine mappings preserve barycentric coordinates. So the question that we asked ourselves was, do locally affine mapping preserve these local barycentric coordinates, and therefore do locally affine mapping define a locally barycentric embedding? So define this kind of map. Is this true? And also, what do we mean by locally affine mapping, and so on? So all the questions. But the idea was to say, maybe we should explore in the direction of affine map to see if something happens. So the answer to this question is yes, under some condition. So yes, local affine mapping will define this kind of embedding. So note back to graph theory, but in a completely different context, so you can forget about the thing that you just saw in the first part. Here we have a directed graph that is defined by the neighbor graph. So there is an arrow that goes to a point to another if the second point is the neighbor of the first one. So it's a directed graph, and on this graph, in the end, we have defined weights that are the barycentric coordinates of one point with respect to its neighbors. So on the second image, if you look at point red, it has 3 neighbors, and to each of the neighbors, we associate barycentric weights that just correspond to the weights within the weighted sum. So that's a weighted and directed graph, and that's the worst kind of graph because it's very hard to study in terms of structure. And here we consider in practice, we kind of mix together the graph, and so which is an abstract object, and the set of points x. So we also speak about weighted sets in the end. Okay, so how is it going to work, the local affine mapping? Well, what we're going to study is defining an affine mapping on each component of the graph and look how they glue, how they are glued with each other. So because it's a weighted directed graph, the natural notion of components is not the usual one, but it's the notion of strongly connected components. So strongly connected components, it's according to the relation of being a neighbor of or this directed relationship. And basically from one component to another, the rule is that you have a way, but you don't have the way back. So that's being strongly connected. So that's the natural notion. And now we're going to explore how this decomposition can reflect a decomposition in terms of affine mappings. So, okay, imagine, take an example, and the worst example where you have 2 disconnected components, so completely disconnected, and you're interested, so you do your step 1, step 2, so you build your neighbor graph, you have these 2 components, and you compute the barycentric coordinates of each point, and now you're looking for a solution that preserves the barycentric coordinates that you have. Then you can, independently, you can transform the 2 components within a affine mapping, and the result that you get with this is perfectly okay in terms of the cost. So it's of cost 0. You have preserved all the barycentric coordinate, and there's no problem. But the thing is, you have a lot of freedom because you have complete freedom of each affine mapping that you can use. So already in this case, you have a lot of solution, and you don't have a unique embedding because all of this work. But that's a very extreme case where it's disconnected. And of course, some people have looked at it already and say, oh, okay, but if the graph is connected, that's fine. But that's not true. So if you get bit more complicated case, so you have two strongly connected components, and they are connected by two arrows here that start at one point. Then for this one point, you will get a condition of how you can choose the two affine mappings, so dependently, such that if you use the two affine mappings, you still get what you want. And this condition is expressed this way. So here is just an example, but the general idea is that you look at the different points that make connections between the two components. Here you have only one to see x1. And then you look at the neighbors of this point, and you average the neighbor of this point to get one condition. So you get a condition, here you get only one condition that is associated to x1. And this condition is expressed in terms of the two affine mappings of each component. They have to coincide at one point. And if you have two affine mappings, you have one condition that still leaves a lot of degree of freedom. So it's not as much as before, but it's still enough to not have a unique solution. But now you have to imagine that you have a lot of strongly connected components. In this case, you have a very general result that we proved, and that says, with few words, it's just that component-wise affine mappings that define locally barycentric embeddings, and of course you have a condition. So you saw the condition in terms of two components. If you have much more components, they are ordered in a way that the arrows are always in the same direction. So you start with the component x1 that's basically as you start with the last component xt, and xt doesn't have any arrow leaving itself, which means that all the points in the component, they have their neighbors in the same component. And then you can go back to the next component that have neighbors in this last one, etc.
You can have a tree.
You have a tree. You have a tree.
It doesn't appear like.
Yeah, it's conceptual notation, but you have a tree.
Oh.
Okay, you could have an arrow that goes like this, for example.
Oh, no, I mean like you can have extremal.
You can have many extremes, yes.
Okay. So it's just in the.
You have, the leaves, if you want to observe tree, are these extremal components. What you know is that you have only at least one, but you can have many of them. So you start with these components, but it doesn't matter if you start if you have xt and xt prime that both of them are extreme. You can start with one or the other. It doesn't change the condition. So you start with these components.
It's a DAG, I think. It's a DAG.
What?
It's a DAG, what you get.
The DAG?
It's a DAG, right?
Ah, yes. Yeah. So you can have a x3 and x4 like this. Then you have a x2 here that does this, and then you have x1 here that does this and this, for example. You have this kind of structure. Yeah. So in this case, you start by an affine mapping of this component and a affine mapping of this component, then you have complete freedom on both of them. Then you're interested in how you can transform this thing. Then you will look at this condition here, you have only one. You will match this condition, it gives you some degree of freedom or not, depends. And then you go to it, and you do this recursively. And in practice, it gives a lot of solution. Because the strongly connected components are not so well connected. So it gives a lot of a lot of solution. And that's the end of this result. What we get from it is that, first of all, we have a better understanding of what is our embedding. So what are our solution? And to be completely fair, what I did here is characterize part of the solution, not all of them. But what I'm saying is that if I do this, then I have a solution. And if I do this, then I can create a lot of solutions. That's the second thing. So from this theorem, we can get a lower bound, some lower bounds on the number of embeddings, for example. And we can even get some asymptotic bounds on the number of embedding if we increase the number of points. And something that is a bit interesting is that even if you get a denser data set, then you get also more solution. So let's say if you thought that sampling better, I don't know, your data would solve the problem, it's not true because it gives more solution.
But how much more? How many more?
Linearly more. So at least, maybe even more, I don't know.
So it's not so bad.
It's not so bad, but I mean, in the end, you still want a unique solution. I mean, that's what they claimed. Okay, so then after, at this step, I decided at some point, I mean, I know, one day I realized that maybe it was not so bad, as you said, to have all these solutions. Because if we have so many solutions, then we maybe can just choose one. If we have the choice, maybe we can choose a better one than the one that they get with the penalization. So from here, I say, okay, we do this, we compute the graph, we compute the coordinates, and then we're going to compute all the solution. So here, that's a point that I didn't mention yet, is that the step 3 in the local linear embedding is very nice because it's worse at an eigenvalue problem. So it's just computing the eigenvectors and eigenvalues of a matrix, which is this matrix, looks kind of like a Laplacian of W. W is the weight matrix, the barycentric coordinates matrix. Here we are interested in our hypothesis in exact solution, only in the kernel then. And so computing the solution that, again, is a set that is bigger than the one we characterize, is very easy. It's a very, computationally, it's not very expensive step. So what we do is that we compute all the solutions that correspond to compute a kernel, and then we pick the solution that, for example, preserves pairwise distances in the dataset the best, but could be another criterion. It could be, I don't know, preserve the statistical distribution the best. But the thing that the theorem says before is that we have the choice. And because we have the choice and they are all equivalent in terms of our first criterion, which was an affine criterion, then let's just introduce a new criterion that is a bit different and choose the best. So that's what we do in practice. And it works very well. So that's just a very toy example, but since everyone uses it, I'm also using it. So classical example in manifold learning, you have the Swiss rule and you want to reconstruct the Swiss rule. Here we chose a bit on purpose a Swiss rule that is not so well sampled. And the criterion that I introduced, the pairwise distance preservation, is more specifically using the distance of isomap. So isomap is a well-known method in manifold learning that actually was published almost at the same time as local linear embedding. And it just says we're going to use the same idea as multidimensional scaling, but no, the distance that we are going to use is a more intrinsic distance because it's the graph distance. So we build the neighbor graph, the same neighbor graph, or a slightly different one. And along this graph, we compute the shortest path distance. And if the graph is well defined, then it should stick close to the non-known, the hidden submanifold, such that our shortest path distance should be close to the intrinsic submanifold distance. So that's isomap. It doesn't work so bad, so I decided to use their distance. And with their distance, I'm picking with all the solutions, the one that works the best. So here are the ground truth. So isomap basically because it works mainly on the distance as a property of preserving scaling very well. So at a global scale, from afar it looks very good. If you zoom in a bit, you see that the scaling of this rectangle is not so bad with respect to the ground truth, but within there is a bit disordered, like. And local linear embedding. So here I'm using their method, so the way they optimize it with the penalization. So it's already implemented in the how is it called? The learning library of Python. I forgot the name.
Scikit-learn.
Scikit-learn. Both of them are implemented in Scikit-learn. So here I really use the parameters so that it's already well optimized. And what you get with the linear embedding is that the scaling is very bad, and you can already see it from the beginning. But in terms of the way the points are placed respect to each other, is not so bad compared to the ground truth. So if you combine now both information, so you take a solution of this and you take the solution of this that preserve the isomap criterion the best, then you get exactly the best of both. That is that you preserve the respective position and you also preserve the scaling. And then when you compare to the ground truth, it's quite good. So this is the method that I kind of got out of my analysis, but in the end, the analysis says a bit more, like it also helps characterize what are embedding. So what are we doing when we compute these weights and reconstruct? So yeah. Well, that's for the second part, and then the conclusion, I don't know, I mean, we can skip it, I guess. Okay, we cannot skip it also, I don't know. No? Okay. So that's the conclusion. So this is what we started with, this is what we did, and also what we did. And there is one part I didn't mention here, is the part where we do the same thing, so local model, but no on a non-Euclidean example. So more specifically, we studied it on the candle-shaped spaces. And it's, let's say it's some technical work because you have to understand how to compute the optimization problem and so on. But conceptually, it's very simple because you just replace your barycentric projection by the barycentric projection, but on a manifold. So let's say to define is very easy. And then the work is mostly about like how to optimize it in practice, how to solve the optimization problem when you have access to only, you don't have access to the explicit tools. So for example, you don't have a way to compute explicitly every Riemann tool and this kind of thing. So you have to also solve equations. So how does it work in practice? And some examples. That's the last part of the work that I didn't present here. And that completes the square. Yeah. And for example, if we look at back to this protein, I just played a bit around with the protein a bit. Okay, we don't see so much, but we have the structure and we are interested in characterizing very simply the configuration of the protein, and the scientists that, both biologists that we worked with, for example, they gave us some work that was to look at the specific two residues where you're interested in whether a sulfur bond will happen between two atoms or not. Not sulfur bond, an hydrogen bond between two sulfur atoms will happen or not. And this can characterize how stable the configuration is or not, basically. So that's just, in the end, you're interested in the position of 3 points, so that's just a triangle. And in the candle-shaped space, everything is well known for the quadratic triangle, like known explicitly. But if you still use the method, so the isometric locally barycentric embedding, to try to reduce the dimension of this set of triangles, then if you look at a one-dimensional representation, what you get is basically a representation where along the line you just have the hydrogen atom that's balanced around the sulfur atom. So that's just a way to interpret a bit more what we do. But that's obviously a very simple example where maybe my method is not the only solution. We could also have computed it explicitly, but that was just to see what it gives on a concrete example. So that's really the 1D-dimensional representation that we get with the methods of our set of triangles using the Kendall metric. And that's not for, yes. And that's, okay, maybe that's interesting. That's for the rest, that's future work. So on theoretical aspects, I would like to explore a bit more the graph space because it's quite new. So we explored it in terms of the barycentric subspace analysis, but not so much outside of it. So it would be interesting to see what does geodesic look like in terms of graph and this kind of question. The theorem, I studied it in the best ideal context where everything is exact, but I would like to introduce some perturbation to this hypothesis, so some error or some noise, this kind of thing, to see if some way still stands. I think it does. I think that even if you have not an exact reconstruction of your point on the barycentric surface, you still have a high number of very good solution, and by very good I mean maybe not cost zero, but very small cost. So I would like to extend it a bit in this way. And I also started to do some trial of embedding in non-linear space, so in constant curvature, like on the sphere. So this is I tried to embed, it's not too bad, I tried to embed a parabolic data set on a sphere. So I had a data set on the parabolic space, and because it's a positive curvature space, I thought, okay, let's try to embed it on a sphere by modifying a bit the method that we had before, and it doesn't work so bad. Practical aspect would be to experiment the two methods on other data sets. So especially for the graph, a very nice application would be brain connectivity, and it's one of the biggest applications in this domain. So, and it's quite a challenge, so it would be nice to see if it works or not. And also in terms more of code, I would like to implement the methods for all spaces. So because right now they are implemented, so they are not online yet, but they implemented one for the candle shape space and the other for the graph. But BSA maybe still need a lot of work to understand if it works for the space. But the way I define the other, so the local method, it's completely defined for any manifold and also any quotient manifold. So I would like to see if I can implement it for other manifold, and if it like work or if it completely crashes down. I would like to see. But yeah, that's a different perspectives. All right, that's it. Take time. So I don't know if you have any questions or not. We can also maybe get more informal and go back to coffee or. Yes.
Did you work with Alice and Nina on the library that you're developing? Do you implement your...
So Nina contacted me like I think 1 week ago. So the way I implemented the method, they are ready for Jumpstart, but I'm waiting for the PyTorch module to be ready on Jumpstart because it relies on PyTorch, and last time we discussed it, it was not ready, so it was not working well. So
that is without
We have different backends, and they're not all the tools that we have don't work for all that.
Yep, so that was the reason. But I encoded it in the same style of Jumpstart, so yeah, we are discussing it with Nina. Once everything is ready, it could be implemented directly on the library. Yes. Yeah.
There are things existing for graphs on Jones.
Anna started, but this is very new, so I don't think there is anything. Although but the candle shape space are already completely implemented. So once, let's say, compatibility with PyTorch is completely settled, it should be fine. I think, yeah. Yes. Okay.
Now I have one question with for the first part, because you said you used orthogonal matrices to relax the constraint of permutation.
Yes.
But usually we say that permutation matrices are external points of mixed stochastic matrices.
Yeah, it's true.
And of course, it's not a group, so it makes no sense. But I was thinking of.
I don't think it makes no sense, but
It's a non-condensed
exactly.
The stochastic matrices, and it's much easier to solve it on SON.
Yeah.
On ON. It's much easier. You have explicit formula.
Okay.
Because
so I agree.
It's really easy.
yeah, you don't have the property that if you would do it on bistochastic, then you would find a permutation as a solution. Because the prime is quadratic.
You would.
You can have this property
I'm not sure.
if you have some assumptions on the cost,
Yeah, exactly.
which is realized in some cases.
But I think not in this one. I'm pretty sure we already, but we can discuss
If
it.
you can embed your data in impedance spaces, it's the case.
Even if the cost,
There is a super nice paper
I know this paper, I'm pretty sure. By Gabriel Perret and Elodie, no?
Israeli people.
Okay.
And it's about reformulation of this graph, isometric graph problem as a concave minimization problem.
Okay.
So you still get an estimate point as a permutation matrix, but the problem is super hard to solve. So you don't gain anything.
Okay, you don't gain.
I mean, you gain a bit, but you don't. I mean,
You should gain a bit, no?
you gain a bit because you relax, okay, but you can resort to non-convex optimization scheme, but you don't have an explicit solution like for SSOM or for OM.
Yeah, I mean, this I think is a bit overkill probably, but I was curious because.
This is not working. You can do it.
Yeah, but what I know with I mean about having an explicit formula, we were not expecting it to start with. When we started with the rotation, it was just to see, okay, we have a simple group, we expect that to have something nice, but maybe not an explicit solution. And in the end, we have it, so it's even nicer. But I'm curious about this because, for me, yeah, okay, I'm curious about the paper. Maybe, yeah.
And I'm sure you know.
Yeah, it's Elodie Maignant.
Yes.
Marwan, okay.
Probably concave graph function.
Probably concave.
Yeah.
It's not always concave. No. Okay. Probably concave. Oh yeah. Everything sees it, but that's fine. Okay. Okay, no, I forgot about the internet working. Okay, that's fine. Okay, I will just give it for later. Okay, and then, but okay, I'm curious about why it works but not so well. As you say.
And there is a paper by computer science guy in the US. I can maybe find it again on your particular organization.
Okay.
And,
Oh.
he's looking at the sort of patterns. Yes, kind of like.
Okay. Yeah, sure. So.
But it could be harder than this.
I didn't say no.
To find it again. Sorry, to find it again.
Because we looked at it was not. I didn't find so much things on this, but at first when we saw the space, we thought, oh, it must have been studied many times because it's so simple.
Yeah, it has been studied.
In terms of the graph, I don't know. Yeah, in terms of the algebra, I know. I'm not worried.
Okay, I'm not sure what you're commenting.
The quotienting the symmetric matrices by a rotation group. Yeah, so we were interested in this too because when we thought it's so easy that it must have been studied somehow. But it has been studied by Peter. That's of course, but
the computer science.
The computer science, yeah, I don't know.
And there are many papers.
Okay, but okay. On the symmetric matrices quotiented by the rotations?
This I don't know.
No, I'm talking about this one. On graph cis, of course, on graph cis. But there's also a lot of literature in geometric deep learning on graphs. But yeah, but it's still, it's still hard. Maybe I'll get the stuff. Sorry. So that I can look at it by myself.
So the book for today,
Yes.